I will begin with a word of prayer to get up here. Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to bless this class today, help us to glorify you when we do, and just understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. So, I realize now I forgot to set the zoom on the camera. If I don't fix this, it's going to be fuzzy. So, do you guys have any questions while I'm playing with the camera here? So we have all agreed that problem 71, right? We will content ourselves to set the problem up and get to the Lagrange multiplier equations, but and then it's good if you tried to solve them, but you should realize after about 10 minutes or so that it's really, really hard. So, and when that kind of thing happens, you could email me, and I would tell you, oh, peace be with you. Go on, do other things. It's too horrible. Unless you just want to really try to solve a problem that's hard. Because such problems exist, right? But anyway, any questions?
Will you offer bonus credit?
I suppose. If you can get past the point I got in the solution, sure. But I think there are probably better things to do with your time, honestly. Yes?
For one of the problems you said graph it. Do we have to draw out the 3D graph?
You can just make a sketch of the 3D graph, or you can print it out, whichever you prefer. Yeah. Now, other questions? I have that announcement earlier for what was it? 3dmath.org. If you want to use that, of course, if you want to, you could, you could use Mathematica, which we do have. MATLAB, you could use MATLAB if you must. No, MATLAB's okay. I noticed in Desmos there's a 3D option. It's in some sort of beta testing phase or something. I haven't tried it yet. I'm curious about that.
It doesn't work awfully well.
It doesn't work good. Drat. Well, that's what's happened before when they've floated a beta for their 3D grapher. So it's actually very hard to do justice to 3D graphing. There used to be about a half a dozen pretty robust website web tools like website-based 3D graphers, but they're all somehow or another linked to the use of Java. So when Java became unsecure, and we stopped trusting academic sites that have absolutely no reason to be malicious to your computer, we lost all of that wonderful work people did because of stupid technology snobbery. But I'm sorry, the well-meaning actions of bureaucrats in IT. But anyway, yes, go on. I love IT. They're great. No questions? All right, well, in that case, let us do some more integration. So your homework is due when? Tomorrow. All right. So I am very proud of the problem involving Dwight Schrute and Kakashi. If you look at my solution to that online, I'm particularly proud of my concept of the Schrute sphere. So if you look at that, it's all about the Schrute sphere. Now it's been questioned why Dwight Schrute can attack in all directions all at once, but it makes sense. Don't question it. The Schrute sphere is achieved with a combination of nunchucks and other, Pennsylvania Dutch weaponry that you'd be familiar with if you'd grown up in the area. But anyway, I had a friend who lived not far from the Scranton growing up, and he had many of the same weapons that that Dwight had stashed around the office if you watched the show. But anyway, so here's an example. Let us attempt, here's going to be a volume, I'll call it E, and it will be x, y, z, such that. Let us do x minus 2 squared plus, y minus 3 squared over 4 plus z minus 4 squared over 9 less than or equal to 1. And I'd like to explain how to set up the volume integral over this solid, all right? And I'd actually like to explain how to set it up a couple different ways. Because there's various ways you could go here. Now, first of all, what is the solid that we're looking at? So let me just describe the problem here. Here's our task. Set up the integral. And let's, for fun, use the function x dv. Did I do x the other day? I think I already did x. Let's do y yz squared. There we go. But really, I could just as well put f of x, y, z there, and everything I'm going to say is going to be the same, because I'm not actually going to calculate this integral. I'm just going to set it up, okay? So let us draw what's going on here sort of schematically. This is a what? This is a solid ellipsoid, right? And so it's, I don't know if I've drawn that correctly or not. No, I have not. If I was smarter, I'd just make it a sphere, but this is not a correct picture in terms of like dimension, so you'll forgive me, but for the sake of you know, what's the word? So this is sort of a heuristic picture, if you will. The center of this ellipsoid is where? See where it is? It's at 2, 3, 4. That's where the formula is based. And we can identify some sort of like vertex points just to kind of guide us, all right? So let's go ahead and do that. What are these points here and here? The blue points that are the furthest they can be in like the y direction. I heard a what?
1 through 4 and 3 through 4?
Nope. We're going to want a 2. We can go plus 2 in the y, so we can go to 5. And we can go minus 2 in the y, so this point over here would be, and I forgot my z. What's my z? What's my z at? 4, right? Because that's in the plane of the center. On the other side, we've got, I'll probably regret drawing this. Let me put the label up here. 2, 3 minus 2, which is 1. 4. Is that what you told me? That might have been what you told me. All right, so they got those 2 points. Now the other 2 points we could think about would be like the highest and the lowest point, speaking of z. So the highest point in z, we'd have x is 2, y is 3, z is 4 plus 3, which would be 7. This point right here, I would have 2, 3, 4 minus 3, which would be 1. Okay? And then you can also picture the points which are furthest in and out of the board in the x direction, right? So those would be, like this front point here, would be what? Our x is 2, but we're going to subtract 1, so we got 1. The y is 3, the z is 4 because it's there. And on the back side, that guy right there, you'd have 2 plus 1, which would be 3, 3, 4. All right, so these are the sort of 4 vertices, if you will. You could view those as sort of radial points in some sense of the ellipsoid. And so if we think about the shadow of this ellipsoid onto the, maybe I'll draw a different picture for the shadow, but basically what's going on here is you've got, if you think about it, like you've got one ellipsoid shadow over here, you've got a different ellipsoid shadow over here, and you got a different ellipsoid shadow down here, right? if you want to think about how this projects onto the coordinate planes, you've got these three different ways to look at it, yeah? So let me start by trying to describe the breakdown of E, where we will start by slicing the x. Right? Let's start by slicing the x. And so, what's my x? What can x do? What is x stuck between? So we look at the green points, right? X is going at smallest 1. Excuse me. I think I've labeled these points backwards, haven't I? So sorry. It usually doesn't matter for my heuristic pictures, but here, at least in principle, it does. So 1 is over here, and 3 is over there, because it's further out in the x, right? Okay, so I have this much. 1 is less than or equal to x is less than or equal to 3. Okay? Now, I should focus for this first one on then what is the shadow. Let's see here. I could do it down here, right? So basically, I've made this and that kind of slice, right? If you like, I mean, it should be parallel. I can't do math. My picture is not, it should be parallel to the x-axis. I've made that kind of chop. Basically, I've lopped off all of space except for this, infinite strip that goes up. Now, I want to get my paws on this equation right here. What is this? That projection. So to get that, I put z equals to what? Excuse me. For the x, that is coming from this equatorial circle right here. I mean ellipse, right? That's the biggest it gets over the xy plane. So that casts the shadow down onto what would be here. So to get that, I put z equals to 4 for this particular solid. So from z equals to 4, I've got x minus 2 squared plus y minus 3 squared over 4 less than or equal to 1, right? That's when z is equal to 4. And so if I solve that for y, what do I get? I get y minus 3. I'm going to solve the equality here, actually. I get y minus 3 squared is equal to 4 minus 4 times x minus 2 squared, right? Which gives me y is equal to 3 plus or minus the square root of 4 minus 4 times x minus 2 squared. Okay, so in order to lop off the rest of space and just leave me with sort of an elliptical cylinder that I have right there, what I want to impose from this is 3 minus the square root of 4 minus 4 times x minus 2 squared less than or equal to y less than or equal to 3 plus the square root of 4 minus, I guess I could pull that 4 out, huh? But, oh well, it's too late. Like that. Okay, so if you can envision in your mind's eye what we've done at this point, if we impose that inequality and then that inequality, what we have then is basically, if I can ruin my picture here, we've got this elliptical cylinder like that. Now I want to cut out just the ellipse. How do I do that? Just the ellipsoid. Well, next up, to cut out the vertical, I solve the original condition here for z. Okay? If I solve that for z, what do I get? I solve this one for z. I get z. I'll do it a step here. Z minus 4 squared. Oops. Z minus 4 squared is equal to 9 times 1 minus x minus 2 quantity squared minus 1/9 z minus 4 quantity squared, like that. All right? And so, finally, I can solve that for z, right? Have I messed up my, oh, I'm sorry, I meant to put y minus, thank you, y minus 3 I meant to put here. Man, you know, these boards are just a mess. It doesn't look like a mess, but the slightest thing smudges them. All right, so that was supposed to be, as you guys told me just a second ago, y minus 3, right? And I had a fourth there, so 1/4 y minus 3 squared, close parentheses. So I've got z is 4 plus or minus radical 9 times 1 minus parentheses x minus 2 squared minus 1/4 y minus 3 squared. And of course, we could simplify things, right? Because the square root of 9 can pull out to be a 3 and stuff like that. I'm not making those simplifications so we can track what I'm doing, okay? I'm resisting the urge to make algebraic simplifications here for the sake of you seeing till the end better. Now we have everything we need. I have described how to cut out the ellipsoid by first chopping x down, and then chopping y, and then chopping z to make my final carving. And so the answer, well, the first answer, is that the integral over e, and did any of this have anything at all to do with yz squared? Not even a little, right? Had absolutely nothing to do with the integrand. This is completely about e, right? Completely about e. And so I would have integral from 1 to 3, integral from, let's see here. So the first shall be first as we're writing it now, but it's kind of funny. The first is first, the second is second, the third is third. That's because these integrals are done inside out, right? So it actually makes, anyway, I shut up. My y was 3 plus the square root. I should really just give it a stupid thing a name, but I'm gonna write it out here. Minus 4 times x minus 2 squared, and then 3 minus the square root of 4 minus 4 times x minus 2 squared. Some of this is bothering you that I haven't pulled the 2 out of that. It's bothering me too a little bit, but I'm just gonna grin and bear it. All right, one more integral. 4 minus the radical of 9 times 1 minus parentheses x minus 2 squared minus 1/4 y minus 3 squared, and then 4 plus the radical of 9 times 1 minus x minus 2 squared minus 1/4 y minus 3 squared. And all of that, inside of that, is my y z squared, right? Now, which one comes first? The dx, the dy, the dz? You guys tell me. I've given you the easy part. Yeah? What? D what? dz is first, because that's the z bound. And then this is the y bound, so we do dy. And then last but not least, x, right? So you guys, continuing this example, how to set up the integral of y z squared. Instead of doing dz first, let's do, oh, I don't know, dx first, and then dy, and then dz. How would you set that up? What would you need to put the bounds to get this integral? See, once I write the order, that makes it unambiguous, right? So let's do it. I'm foolishly going to attempt this without writing so much. All right, I'm just going to try to write down the answer, and we'll see that I can't do it because you have to do some work. But I'm going to try. We'll see what happens. So you guys help me out. What would the last shall be first? The dz integral. That's the one that's the last. That would go from 1 to 7. And it occurs to me that really everything that I had, everything I have here in this big green circle, right? The analog of that for this case basically boils down to what? Thinking about, let's see here. I got to think about x and y.
Still set for y just in terms of z.
Is that it?
Is y still the middle?
Is it still the same? Still the same ellipsoid, huh? I mean, still the same ellipse. Still the same elliptical shadow I'm thinking about. That's funny. Okay, so let's see here. So next I want my y in terms of z, you said? I'll believe that. So integral, let's see here. Well, maybe. Let's see here. So I'm trying to visualize it for a second. So this is my z. I need the y bounds to go here, and my x bounds to go here. This is my z bounds over here. So I just have a mental block because I don't want to believe that what I circled in green can be exactly the same. What's the word? Thought process here. Like it feels like since x is playing the role z did in the previous one, I should be looking at the shadow onto the back one, which I don't think you're disagreeing with, Sam, right? Like it's not this circle, it's not this ellipsoid that matters anymore. It's essentially this one right here, right? That's playing the role that previously the ellipse in the xy plane did. So, you know, as I think about that, what is the shadow back into here, right? From the ellipsoid, like where is that coming from? Where's the biggest, as you think about the projection of the ellipsoid, right? If you think about the projection of the ellipsoid back onto the zy plane, right? Of which x is normal to. What circle is it that what circle is it that determines that largest shadow as you just project back directly onto the coordinate plane? Can you guys tell me? Y equals 3. That's where it's coming from. Y equals 3. Ooh, I think I disagree. I think it's this one here. See, we looked at z equals to 4 to get that one down here before. Okay? Remember, we looked at z equals to 4 to get that. Now we're going to look at x equals to 2 to find the largest ellipse, which projects back onto my YZ coordinate plane, because that's the elliptical cylinder we're going to want to cut out, and then from that we're going to cull out cut out the shape from that. So I need to figure out what that is, and that is what comes from setting x equal to what I just say. I can't remember. 2, x equals to 2 gives me that one. X equals to 2 gives me the projection, gives shadow. See, because we have to figure out what's the largest that the volume is in that direction. And the largest that the volume is, if we think about the x direction, about all of the, all of that is just that elliptical cylinder. That's like as big as it gets. So if we can cut that out, then we can go from there to cut the rest of it out by limiting x in terms of a radical function involving y and z. So, okay, so getting to the point here, if I put x equals to 2, this shadow basically is governed by the original equation, but with the x term gone, right? So you just have y minus 3 squared over 4, was it? Plus what? Z minus 4 squared, what over, is it, what I put there? I can't remember. 9? Did I put a 9 there? Less than or equal to 1? So, this in particular, well, we already kind of judged, I already kind of told you what's happening, that z, I did my z last, right? So I'm telling you that the z goes from where? From 1 to 7, right? I already kind of stole that thunder already, but that's here as well. And on the other side, the side pieces there, how to bound the y in terms of the z, these right here, the tricky ones, right? The minus and the plus. That's going to give me, let's see here. I'll get it eventually. Y is equal to, well, 3 plus or minus the square root of 4 times 1 minus 1/9 z minus 4 squared. If I done that correctly, I think I have. So I have to put those here. So 3 minus the square root of 4 times 1 minus, come on, 1/9 z minus 4 squared, 3 plus the square root of 4 times 1 minus 1/9 z minus 4 squared. All right. Okay. Cool. That's it for the y bound. And then finally we worked our way, and it's, in some sense, it's funny that the most complicated bound is actually kind of the easiest one to think about, really. Because the most complicated one, you can just go back to the original defining equation and just solve it for the variable in question, which in this case is x. So solving that for x, I get, 2 minus the square root of 1 minus, what was that? 1/4 y minus, goodness gracious, 3 squared minus 1/9 z minus, oh, thank you. If I could just remember my problem for 3 seconds, that'd be wonderful. And then up here we've got 2 plus the square root of 1 minus 1/4 y minus 3 squared minus 1/9 z minus 4 squared, like so. And then inside, the easy part, the very easy part, yz squared. And then what comes first? I guess I already had it over there, right? Dx, dy, dz. Now, it takes me a while to think through these when they're more complicated like this, especially if I personally don't find setting up integrals in the way I just did most natural. Like, my default is to think in terms of, I want to understand how to limit z, and then, basically use x and y as the more complicated part for limiting the variables. But we should, at least in principle, be able to set it up any of these different which ways. Can you guys tell me how would you, if I flip the bounds, let me not write it all out, but what if I still had, you know, integral, basically y z squared dx dz dy. How would the story change if I was doing it that way? One thing you should be able to tell me without much work at all is that, oh, well, so x still is what? I mean, the innermost bound is still just what it was before, right? So the inner bounds, let me call this Pac-Man minus, Pac-Man plus. So, you know, it's still integral from Pac-Man minus to Pac-Man plus. But then, and I'll do the other easy part, the other easy low-hanging fruit, it would be the outermost bounds, which is what? What would the y range over? What's that? 1 and 5. Y goes from 1, yes, 1 and 5. Very good. Now, to figure out the others, you know, we'd actually have to do what? You have to go back over to here, right? Really to here. And instead of solving for y, solve for z. But same, more or less setup. The other two ways to do this are based on what? The other two ways are based on using y in the role that x was just playing and that z was initially playing. So to do those integrals, we'd have to think about the projection of the ellipsoid back onto, you know, the xz plane, where y is playing the normal. So like that, if you look over here, we'd be thinking about slicing out a cylinder of space based on this projection, right? Which would be based on, finally, this circle right here. Well, it's not a circle, of course. This ellipse right here, which would be what? This is where y is equal to 3, and we've got what? The equation x minus 2 squared plus z minus 4 squared over 9 is equal to 1. So in view of that, the other way to do this integral, y squared, yz squared. Let's see here. I'm trying to do which one. I want to do my y last, so let's say we'll do dx dz dy. All right. We haven't done that yet. Yes. Then this would be what? The integral. So my y integral comes last. The y bounds go from 1 to, what is it? No? 1 to 5. And then the integral over z, I think about, you know, solving that one for z. What do I get? I get for the man, sorry, I keep losing my place. Rats. Well, I can do the inner one. The inner one's easy. That one we just solve for the x. I think I had that before somewhere up here, right? Oh, we already have a name for that, don't we? So, yeah, Pac-Man plus Pac-Man minus, and I've got my y z squared dx dz dy. This is the tricky one. What do I put there? Wait a minute, have I done, I just did this. You guys gotta stop me. I'm like, this feels really similar. Yeah, it's because it's the same stupid case, I just did it. I'm a dummy. All right, if I could do this correctly, y is the last one. So I meant to put dy in here. Y was here. So then we put, you know, dz and dx like this perhaps. All right. I'm trying to show you all of the different cases for at least one example, because you should see what it looks like for one example. All the cases. It is a pain. Now, this becomes easier if instead the volume is something simple like the one we did last time, where it's just, you know, the coordinate planes cut off by like an interesting plane. That becomes easier to set up than this, but I think it's good to have a hard example, so that's what we're doing. Anyway, okay, so, all right. The x one, do I have this? All right, so the last here is my x bound. So my x goes from what? My x goes from 1 to 3, right? Then I've got the trickier one. The least tricky is the inside one, y, because I just solved that one for y. I get what? 3 plus the square root of what? 3 plus the square root of 1, man, I can't see anything. 4 times 1 minus x minus 2 squared minus 1/9 z minus, what we got? 4 squared, like that. And then down here 3 minus that radical, which I probably should have given a name, but it's too late. All right. Let me not forget my yz squared, and we've got our dy, dz, dx in here. So my dx ranges from 1 to 3. My y ranges from this to that. Now, some generic features we should be looking for in the bounds for them being logical. Like, let's just take a step back. There's some simpler things we can observe in the patterns for all the answers I've written on the board. Can you guys point out any of them? Like, as we look at the bound here for y, right, which is this ugly looking radical expression here and here, what letter is missing? Y, right? You can't use the letter that you're bounding in the bound expression. Notice that's also true up here. X is the bound. We're bounding x with the most ugly one. As you notice, there's no x in the Pac-Man plus or minus, right? And if we go back to this one over here, z was the inside integral bound, right? You notice that there is what? There is no z in that inner bound. And in fact, if you work your way out, how about the y bound? Can there be any y in the y bound? Nope, there's just x's. If we look at this one, in the z bound, well, we're not there yet. If we look at this one, in the z bound, oh, sorry, if we look at this one, in the y bound, as you notice, there's only z's, right? And we already used up the x in the previous step. That's another rule. As you work your way inside out, you can't have variables in the outside bounds which you've already used up in the inside integration. This is something to notice to make sure that you're actually on track. Because if when you do these integrals, at the end of it you've got like a floating free variable of x, y, or z, you did it wrong. All right? These integrals are numbers. They could be -1, they could be 1, they could be 0, whatever, but the answer is a number. These are definite integrals. All right? So you guys, what should I put here? It goes back to this right here, right? I solved that for what variable? I'm trying to bound my z's. So it looks like I've got, what do I got? 4 plus the radical 9 times 1 minus x minus 2 squared. 4 minus the radical 9 times 1 minus x minus 2 squared. Did I do it right? I'm asking. See, so when I actually compute this y integral, I'll have a function of x and z. The y integrates away, right? So you'll have an integrand which is just x and z. And then you're doing integration over z. But the bounds are in x. Well, that feels right for me. So if I haven't made some stupid sign error, that should be correct. There is yet another way to do this, right? Because what could you do? You could take the last one I did, and instead of doing, you know, instead of doing dz dx, you could do dx dz, right? And if you did that, that would flip the what? That would flip these two around, in the sense that instead of going from 1 to 3 for your dx, you would take your dz from what? 1 to 7. And you'd solve this here. Anyway, I hope I've convinced you this is not something you can just like cavalierly go, oh, I look at this and I just shift this around and put this here and there. Like, that's not how it works. You have to think through this junk in order to get it correct. Like, you can't just wing it. There's no simple, oh, I just look at one and I just write down the other 5. Like, no, at least I can't. I have to think through the geometry of what I'm up against, which is a genuinely 3-dimensional problem. And that's why this is hard. It's not because the integration's hard. The integration's not hard. That's not the hard part. The hard part is setting these up. Do you guys have any questions before I find one that's not so horrible to do? Yeah.
Do you often require us to think of symmetry and tricks like that to get, so like for this we can have 8 times 1 1/4 or 1 quadrants of the length, or something like that.
Well, yes. Ultimately, we will find better ways to do it in terms of we'll introduce other coordinates, like elliptical coordinates. Or, like you said, if there's a symmetry of the problem, then wonderful. We could like exploit that and chop our work by 1/8 or something, right? However, with something like this one, I don't think there's any symmetry for this one. Why is that? Do you guys see why there's no symmetry for this one? If I was actually to calculate these horrible, horrible integrals, what would I be up against? See why there's no symmetry here? The function we're integrating, yz squared, it's not really nicely centered about the, you know, what's the word? It's not nicely centered around the center of the ellipse, the ellipsoid, right? So like any hope for like some sort of symmetric calculation is spoiled by the fact that my integrand does not bear the same symmetry as the volume over which I'm integrating. See, there's no pairing between the integrand and the volume. And that's like the first thing with a symmetry argument is we need there to be like a balancing between the expression we're integrating and the actual region we're integrating over. So I need to get the projector out for a second here so you can't accuse me of just doing one example in all the class. Because then, of course, this will be levied against me as, how dare you ask this question on the test? It took you a whole class to work one of these problems. Well, yes, it takes me a long time to explain it, but once you understand it, you ought to be able to do these in less time. Certainly than me doing what I just did. So here's an example. Here our shape is less formidable. And we're graphing, well, I haven't even graphed it, have I? But if you guys could envision what the graph is here, could you tell me what it is? X goes between 0 and 1. And what else do we have? 0 less than y less than x. And z is between x and 2x. What's going on here? Yeah. It's like a quarter pyramid, something like that. It's got flat sides. It's bounded by planes. If we had more time, we could try to picture it, but we're just about out of time here. So I just want to point out to you that you can also do these calculations without actually drawing the picture, which is also kind of neat. So for this one, it's very friendly the way this has been characterized, right? Because the way the volume is set up for you, it already yields itself to setting up the integral, right? So I need to do what? I definitely need to do the x bound last, and I definitely need to do, the y bound first, since it's, well, I guess I got choices. I could either put the z on the innermost integral, or I could put it, I got two different choices here, I suppose, but anyway, I did it as I did it there, so. In any event, I hope you learned something today. If not, I'm sorry, but we will do more tomorrow. We're not done.